Welcome back. In the last session, we started subject-wise test 1 problems and we were solving problem number 8 and 9 linked answer problem, and we were in between while solving the problem number 8. Okay. If I just recollect what we had seen in the last session, this is what is the circuit which is what is given. The PMOS gate voltage is fixed, therefore source voltage is also fixed because of power supply, therefore the VGS of PMOS is fixed. But the VGS of NMOS is varied because this is what your variable voltage. Now, the question of 8th one is nothing but when VG is increasing beyond 1 volt, what are all the regions of your MOSFET? And I explained that when VG is 0, I am starting from 0 till 5. Let us say when VG is 0, what are all the regions? When VG is 0, your VGS of NMOS is 0, your NMOS is in cutoff state. Therefore, this is open circuit. Therefore, surely your PMOS, because if you take a capacitor here, you are always for MOSFET or CMOS inverter, the load is capacitive because the output will be driving to 2 gates or 1 gate, whatever it may be. Therefore, that will have some gate capacitance, ultimately capacitance. Your PMOS, through PMOS, the 5 volt will be charging, means using 5 volt, it will be charged to 5 volt. Therefore, this is what your 5 volt. Then what is your VDS of your PMOS? VDS of PMOS is 5 minus of minus 5. Actually, this is what is drain. Okay, for your PMOS, this is drain, this is source. For your NMOS, this is drain, this is source. Okay. Therefore, the drain is 5 volt, source is 5 volt, VDS is 0. Therefore, this is in linear region. Now, the problem is when VG is greater than or equal to 1 volt. Why 1 volt? Threshold voltage is 1 volt. When till 1 volt, your NMOS is not conducting. It is off only. When this is what is off, your V0 is approximately equal to 5 volt. Therefore, now tell me, the moment when VGS is slightly greater than 1, the moment when VGS is slightly greater than 1, then what will happen? Your NMOS starts conducting. Whether it is in linear region or saturation region, that I will tell you. But it will start conducting because channel formation happened. Because your VG is slightly greater than 1. Then your VGS is slightly greater than 1. You can say approximately equal to 1. Then your NMOS started conducting. But what will be your VDS? Just before 1 volt, your VDS is 5 volt. The moment NMOS starts conducting, right? NMOS starts conducting. Then what is your VDS? VDS will be almost 5 but less than 5, but it is almost close to 5. Your VGS is almost 1 volt. Your VDS is almost 5 volt. Then what is the region of the transistor? Therefore, if you take NMOS, right? Then what is your VGS? Your VGS is greater than or equal to 1 volt. Then what will be your VDS? Your VDS will be close to but less than 5 volt. Then what is the region of the transistor? VDS is 5 volt. Therefore, if VDS is greater than or equal to VGS minus VT, therefore, what is VDS? Close to 5. What is VGS? Close to 1, 0. Is this true? Yes. Therefore, NMOS is in saturation. Your NMOS is in saturation. What about PMOS? If you take PMOS, what is your VGS? Mod VGS, that is fixed. It's not changed because the gate voltage is 3, source voltage is 5, your VGS is 2. But what is your mod VDS? It is also what? Close to 0 but greater than 0. Why it is close to 0? Because when there is something, then there is a current, there will be a small drop across RP, but the current is very small because the VGS of NMOS is slightly greater than 1. Current is very small, the drop across RP is also very small. It is V0 almost equal to 5, but it will be 5 is equal to this voltage plus this voltage. If there is some drop, that V0 will be slightly less than 5 volt. What it may be? V0 will be slightly, but what is VDS? VDS is almost 0. Then what is the region? This is still what? Linear region. Then what is our circuit? Your circuit will be what? Your PMOS will be in linear region. Therefore, this is what people call your PRP, and your NMOS is in saturation. This is what is this. And this is what is your V0. And this is what is your 5 volt. Therefore, this is what is linear region. Your PMOS is in linear region. PMOS is in linear region. And your NMOS is in saturation region. Therefore, what is the answer? If your VG is slightly greater than or equal to 1 volt, your NMOS from cutoff state to saturation state. Here, your PMOS is in linear and your NMOS is cut off when VG is 0. NMOS is in cut off. Strictly speaking, not only VG 0, VG less than 1 volt also. That is also true. This is cut off. Okay. Therefore, your PMOS region is not changing, even though you are increasing your VG beyond 1 volt. But your NMOS from cut off state to saturation state, it is entering. Therefore, cut off to saturation, it is directly entering. Okay. Therefore, what is the answer? Problem number 8. The answer is NMOS is in saturation and PMOS is in triode region. Triode region or linear region. Therefore, answer is D. Answer is D. If you know this, then only you can solve problem number 9, because this is linked answer problem. Okay, take it. Then we'll see problem number 9. See, for MOSFET problems, if you know the regions of the transistor, then only you can equate your current equations and all those things. Therefore, knowing the regions of transistors is compulsory to solve MOSFET problems. Now, write down problem number 9. Estimate the output voltage V0 when VG is equal to 1.5 volt. Therefore, what is problem number 9? What is V0 when VG is equal to 1.5, which is slightly greater than 1 volt. Actually, to find V0, we should know the regions of the transistor. We know, right, what is NMOS? NMOS is in saturation, PMOS is in linear region. Whatever it may be, now we need to find V0 only. Okay, whatever it may be, the current from PMOS is equal to current from NMOS. That I can say, right? Therefore, your PMOS is in linear region, right? Therefore, the ID of PMOS, right? Therefore, IDP of PMOS, which is in linear region, right? IDP linear mod is equal to the drain current of NMOS, IDN, which is in saturation. That is what we got. No need to mod because that is positive. That's fine, right? Therefore, what is ID linear? What is ID linear of your PMOS? Is nothing but mu p Cox W by L into VGS minus VT, mod VGS minus mod VT into what? Mod VDS. This is for PMOS. Okay, let us say mu only. This is for PMOS. Should be equal to, what is IDN of, like what is current of NMOS when it is in saturation? right? Therefore IDP is equal to IDN, but IDP is nothing but linear current, IDN is nothing but your saturation current. Therefore what is the saturation current? Mu into Cox W by 2L for saturation into VGS minus VT whole square. This is what is for NMOS, because in series current is constant. If you solve, you will get it. I think mu n Cox W by L will be cancelled. Even it is given, but cancelled. This will be cancelled. This will be cancelled. 1 by 2 is there. Therefore, what is your mod VGS? Mod VGS of PMOS is nothing but 2. And what is mod VT? Mod VT of PMOS is 1 into what is your mod VDS? Mod VDS is nothing but, what is your mod VDS? Drain to source voltage or source to drain voltage, anything is fine. Therefore, we know that always source is more and then drain. Therefore, mod VDS is nothing but what? 5 minus, because we want only magnitude, 5 minus V naught, that is nothing but your mod VDS. Therefore, 5 minus V naught is equal to, what is mu n Cox? That's gone, 1 by 2. What is VGS of PMOS? VGS is given 1.5 minus VT 1 whole square. Therefore, this is nothing but 5 minus V naught is equal to 1.5 minus 1, 0.5, 1 by 2. 1 by 2 is nothing but 1 by 2 square. 1 by 4. 1 by 4 means 1 by 8. Therefore, what is your V naught? V naught is equal to 5 minus 1 by 8. 1 by 8 is nothing but what? 0.125. Therefore, this is nothing but 4.875 volt. This is what is your V naught. It is close to what? It is close to 5 volt but less than 5 volt. That's what I told, right? If you take here, what is your VDS? This one. This is what is close to 5 but less than 5. Then what is your mod VDS? Mod VDS will be 0.125. This is what is 0.125. It is close to 0 but slightly greater than 0, which is 0.125. Satisfied. Therefore, what is the answer? 4.875. But answer is given like 4 plus something, right? Definitely 4 plus something. Therefore, answer is either B or D. What is 1 by root 2? 1 by root 1.414. And what is root 3 by 2? 1.7 by 2. Yes, I think D is satisfying. I think you can check it. Therefore, answer is D. This is nothing but, this is also same as 4 plus root 3 by 2. Therefore, answer is D. Both are D only. Okay. Take it. After that, we will solve problem number 10. I hope everybody understood the procedure. If you want to solve second bit, the 9th problem, you should know the regions of transistors. Once you know the regions of the transistor, you equate the currents, because currents are same, because those two are in series. Then if you equate, you will get the one. Okay, done. Now problem number 10. Problem number 10. For N-channel MOSFET circuit shown in figure, the threshold voltage is greater than 0. VTH is greater than 0. The source voltage VSS is varied from 0 to VDD. The source voltage VSS is varied from 0 to VDD. Okay. Neglecting channel length modulation, saying that lambda is 0. The drain current ID with respect to VSS. What is ID with respect to VSS? That is the problem. The circuit is, this is what is the circuit, and this is what is the battery, and this is what is your VSS varied, and this is what it is. This is what your VDD. Okay. Now, very simple. I think this is straightforward. We have all 4 options. Like curve, what is ID with respect to VSS? Okay. Now, tell me, he said that VTH is greater than 0. That is expected for N channel enhancement type MOSFET. Threshold voltage is positive. Now, we know ID, right? This is in saturation because this is diode connector transistor. Therefore, your MOSFET is in saturation. When transistor is in saturation, what is your ID? ID is equal to mu n Cox W by 2L into VGS minus VT whole square. Right? Qualitatively I can explain, quantitative also I can explain. What is qualitative part? Qualitatively, right? Therefore tell me, therefore what is VGS? Your gate to source voltage, right, is equal to the gate voltage minus source voltage. What is gate voltage? Your gate is connected to VDD. What is your source voltage? That is connected to VSS. Right? Therefore tell me, as the source voltage VSS is increasing from 0 to VDD, that is what given. As VSS increases, then what about your gate to source voltage? Your gate to source voltage, because as this is increasing, your gate to source voltage decreases. Therefore, your gate to source voltage decreases. When gate to source voltage is decreasing, then what will happen? Your ID also will decrease. Therefore, your ID decreases. But how is it decreasing? It is decreasing non-linearly because it is VGS minus VT square. When VGS is decreasing by some value, but your ID decreases non-linearly. Whatever option you have, therefore let us say this is what is my VSS. Because ultimately we are looking for what is change in ID due to VSS. This is VSS and this is ID. It has to decrease non-linearly. Very simple. It has to have like this. What is the option which is satisfying that? See, option A, option D saying that your ID is decreasing. But option D is saying that ID is decreasing linearly. But we know that it will not decrease linearly because of the square term, non-linear term, right? Because this is non-linear. Right? Therefore, answer A is correct. This is what is using qualitative analysis. But if you do quantitative analysis, what is your ID? ID is equal to mu n Cox W by 2L into, what is VGS? We already see, right? Gate voltage, which is nothing but VDD, source voltage VSS minus VT whole square. Therefore, this is nothing but a constant Kn by 2 into, can you write it as VDD minus VT, which is constant, minus VSS whole square. Now as VSS is increasing, now you think from this equation, right? Now this is what is your VSS and this is what your ID. Now when VSS is 0, then ID is nothing but VDD minus VT whole square. That is the maximum. Okay? But when VSS is equal to what? It can go to what? It can go to only VDD minus VT only. When VSS is equal to VDD minus VT, then ID will be 0. Because When gate voltage is VDD and this is what is VDD minus VTH, it will have VTH. When this is more than VDD minus VTH, it will be less than VT. Your transistor will be completely off. Therefore, it is non-linearly decreasing and it is becoming 0 when this VSS is becoming VDD minus VT. Then your ID is equal to 0. Therefore, this is what is our VDD minus VT. I think from this I can say what is the answer? Your answer is A only. That is what it is satisfying. When VDD minus VTH, your current is 0. Okay, done. Take it. Then we will see problem number 11. This is what we are trying to analyze. VGS decreases, your ID also decreases. We'll give you 30 seconds more, then we will see problem number 11. Done, right? Now write down problem number 11. One input terminal of high gain comparator. One input terminal of high gain comparator circuit is connected to ground. Let us say this is what your comparator, open loop op amp is nothing but your comparator. Okay, let us say this is what is connected to ground. And a sinusoidal voltage is applied to other input. And here a sine wave is connected, let us say. Okay, then the output of comparator will be straightforward. This is what your input, let us say, right? This is a comparator. When input is positive and VA is greater than 0, right, your V0 will be, because plus, let us say this is what is plus VCC and or plus VSAT or minus VSAT, okay, minus VCC, what it may be. Therefore now when VA is greater than 0, when this is what is positive, plus is more, then V0 will be VCC. When VA is less than 0, okay, then what is your V0? Because minus is more, you will get minus VCC. It is a comparator, right? Therefore when you apply a sine wave, now what is your output? For the positive half cycle, right, means if you get the transfer curve, ultimately transfer curve, What is transfer curve? This is what is your Vi and this is what your V0. It will be like this. Plus VCC minus VCC. Okay. Now, once you have that, what is your output? Now, this is what is your 0. Therefore, tell me, when VA is greater than 0, your output is plus VCC. When VA is less than 0, minus VCC. Therefore, tell me, what is the answer? Square wave. Sine to square wave converter, a Schmitt trigger with same switching point. Therefore, answer is D. It is a square wave. Done, right? After this, problem number 12. It's a simply comparator. But he didn't say that apply input sine wave only at plus. You can apply here also. Then for the positive cycle you get minus VCC. For the negative cycle you get plus VCC. Whatever maybe you will get square wave. Whether it is having inversion or non-inversion, that depends on where are you applying your input. Okay. He didn't speak about all those things. When you apply sine wave, what is your output? Square wave. Done. Right. Now problem number 12. The first dominant pole encountered in frequency response of a compensated op-amp is approximately. I think we already discussed in the last sessions, right? See, after frequency compensation using Miller capacitor, after frequency compensation, right? If you take root locus, earlier we had, let us say, P1 and then P2, these are all dominant poles, but after frequency compensation, I told, right, pole splitting, your P1 will move towards origin, and this is what is becoming dominant pole. Therefore, the value is around, this is nothing but dominant pole, and I told that is what is having around 5 Hz. Therefore, using this, if you ask me what is the frequency response of your op-amp, compensated op-amp, which is there, the composition is there inside. Okay, this is what is one pole system. Now, this is dominant pole system. Your op-amp is dominant pole system. After compensation, using compensation capacitor CC, which is there inside. Okay, then if you ask me what is the frequency response, the frequency response of your dominant pole will be, because what is your pole frequency 5 Hz, Bode plot. What is Bode plot? This is what your Bode plot. Therefore, and this is what is your differential gain magnitude. Therefore, this is what is your first pole, therefore, which is 5 Hz. This is what is your first pole, P1. P1 is moving towards origin, right? This is nothing but your frequency. And then second pole will be, and this is what your unity gain frequency. This is what your unity gain frequency. This will be in the order of 1 MHz. If you take IC741 op-amp, this is what is 1 MHz. Your P2 will be somewhere here, which is non-dominant. This is non-dominant. This is non-dominant. That's why this is called dominant pole system. This is non-dominant. Non-dominant pole. And this is what is your dominant pole. Your total response is dictated by the dominant pole only. Dominant pole. Therefore, what is the answer? Your answer is, the first dominant pole encountered in the frequency response of a compensated op-amp is approximately 5 Hz. Actually, this is the bandwidth. Answer is A. Therefore, what is 3 dB bandwidth? This is unity gain frequency, right? Then this is nothing but your 3 dB bandwidth. Therefore, 3 dB bandwidth. Bandwidth means 3 dB bandwidth is nothing but 5 Hz for open loop op-amp. For open loop op-amp without feedback, okay? But it has compensation inside. But when you apply feedback, what will happen? Your gain will decrease, but your bandwidth will increase. Your 3 dB bandwidth will increase, okay? And if you ask me what is the gain, your gain is nothing but 2 into 10 to the power of 5, which is nothing but 106 dB. This is what it is. That is for IC741 op-amp. That is approximately 0. Actually, it is close to 0. That is the bandwidth, open loop op amp bandwidth. Done? That is what is problem number 12. If that is over, then we will see problem number 13. I'll give you 30 seconds time. After that, we'll see problem number 13. Done. Okay. Problem number 13. The most commonly used amplifier in sample and hold circuits. What is sample and hold? The name itself is saying sample and hold. We need to sample and hold. See, for sampling, whenever you want to sample, right? Let us say there is a signal. Let us say a sine wave. This is what is continuous signal. This is continuous signal. If you want to sample, whenever you want to sample a voltage and then hold. What does it mean? Whenever you want to sample and then hold. Therefore, when you sample this, you have to hold it. Again, whenever you sample this, you have to hold it till the next point. Therefore, this is what is called sampling. When I say sampling, your input is equal to output. Your output is equal to input. Can you say that? Your output is equal to input. Therefore, whatever it may be, it has the previous value. The moment when you are trying to sample, whatever input you have, that should be your output. The black one is nothing but your input. Now the blue one is nothing but whenever you sample, okay, then that should be hold. Again, whenever you sample, then that should be held. Again, whenever you sample, here let us say, whatever input you have, that should be held. Whenever you sample, then whatever you have, it should be to input and it has to hold. Whenever you sample here, then it will come here. Whenever you sample here, let us say, then it has to hold and it will come here. And whenever you sample here, then till this point, okay, now it will hold and then it will come here. Therefore, it is what is tracking your input but sampling and then holding. Then what is hold here? Hold is nothing but, this is nothing but hold, right? Hold is nothing but storing sampled value, sampled analog value. How will you get it? Okay? And therefore, if you see here, sample and hold, it's very simple. Sampling is nothing but what? There is a switch. This is what your input. Whenever switch is on, the input will be going to here. But whatever voltage, when switch is off, because I need to hold it, right? Sampling is done. What do you mean by sampling? Close the switch, the input will come to output. Fine. But the switch is open because switch is closed only in the sampling point. Right? Therefore, when switch is open, it has to hold. That is nothing but what? Your capacitor. Capacitor is the one which is what is storing your analog value. It's not digital storage. It is analog storage. Therefore, when you close the switch, your input will be going to your output. When you open the switch, your capacitor will hold it. And once you have this, it has to be buffered. Buffer means this is what is your buffer amplifier. Your buffer amplifier. And this is what is your actual output. This is what is your output. Why you need buffer amplifier? If there is no buffer amplifier, then if you connect directly load here, therefore definitely you are going to some load circuit, then this load should not impact your capacitor, storage capacitor, whatever you have. For example, if buffer amplifier is not there, then this load whatever you connect here, then when you close the switch, the input, instead of simply charging your capacitor, it is what is, we have to do something for the load also. Therefore, indirectly loading is affecting your action, which we don't want. That's why I told you, to avoid a loading effect, put or insert buffer in between. Therefore, because the input impedance of your buffer is very high, that is what is infinity, and output impedance of your buffer, I am speaking with respect to voltage, 0, then whatever you have here, the same thing will come here. That is what we want. Whatever you are sampling and then holding, that has to be given to your load. Therefore, this is nothing but we should have a voltage gain is equal to 1. We want voltage gain to be equal to 1. Therefore, we can use non-inverting buffer amplifier. Then what will you do? For practical implementation, this is what is done using a MOSFET switch, and this is what is our control signal, which is what is sampling whenever you want, and this is what your storage capacitor. Then once you get the voltage, give it to a non-inverting buffer amplifier, minus plus, then this is what is your output V0, and this is what is your continuous signal. This is your continuous signal, and this is what your control. This is nothing but your sampler, and this is what is your storage capacitor or holding capacitor, and this is what is whatever input you are giving here, the same voltage you get here. Therefore, this is what is having a voltage gain, AV is equal to 1. Therefore, this is what is sample and hold. This is what is sampling, and the voltage is hold. We are holding here, and this is what is buffering. This is what is our buffer passing to your load. This is what is our real load, actual load. Okay. Therefore, what is the answer? In sample and hold circuit, the amplifier used is unity gain non-inverting amplifier. This is what is unity gain non-inverting amplifier. Therefore, what is the answer? Your answer is B. Answer is B. Now, problem number 14. In the figure, assume that op amps are ideal. The output voltage of the circuit is this is your Vs. What is Vs? Vs is equal to 10 cos 100t, 10 ohm, 10 millihenry. Okay, and this is what is point number 1, point number 2, and point number 3. This is what has given. Okay, asking for what is V0. Okay, now strictly speaking, I can explain the problem qualitatively. Qualitatively means, if you observe clearly, this is nothing but what? Applying at the resistor and an inductor, right? Resistor and an inductor. Therefore, this is indirectly what? This is nothing but, actually, let's okay. Resistor and capacitor. This is low pass filter, exactly reciprocal. This is high pass filter. Therefore, what it will be? This is nothing but your differentiator, and this is what your integrator. Differentiation and then integration of any signal. Signal, differentiation, and then integration. Therefore, differentiation integration will be cancelled. Almost you will get V0 is equal to your Vi with some gain change. Therefore, V0 will be equal to Vs only, because this is what is your differentiator, and this is what is your integrator. Therefore, tell me, if you take two blocks, one is differentiation d by dt and another is integration, then this is your Vi, then V0. Then what is your V0? Your V0 will be equal to Vi only with some gain change. Okay, using qualitatively, if you see the options, by seeing the options, B is having integration, C is also having integration, D is also having differentiation. No, without any differentiation, without any integration of your input, is nothing but option A. Actually, answer is A. But let us solve, right? It's not to find, let us say it is a fill in the blank. Then what should be V0? It is similar to your Vs without any differentiation integration, but your 10 can change, right? Gain can change. We don't know that value. That depends on your R value, RC value. Let us calculate. Okay. Now, this is what your V1, right? Now what I do, let me call, because both are a negative feedback, this is what is 0 volt, and let me call this is what is V2 only, and this is what is 0 volt. Let us apply nodal analysis. You'll get the answer. Okay. Now let's see. When you apply nodal analysis, what you get? 0 minus Vs, or you know, right? This is nothing but what? V2 divided by Vs. What is V2 by? Minus Zf divided by Z1. R2 by R1, right? Therefore, V2 by V1. We know that V2 divided by Vs. V2 divided by Vs is equal to minus Z2 by Z1. S into L divided by, let me call this as R1, R which is nothing but 10. Right? Now, therefore, what is your V2? Therefore, V2 is equal to minus S into L into Vs divided by 10. This is equation 1. Similarly, from the integrator, what is V0 divided by V2? V0 by V2 is equal to 1 by SC divided by 100, which is nothing but minus 100 into SC, right? Therefore, what is your, this is nothing but your V0. Therefore, what is your V0? Therefore, V0 is equal to minus V2 divided by 100 into SC. This is what is equation 2. From 1 and 2, what is your V0? Therefore, your V0 is equal to, substitute V2 value this, minus into minus, plus your V2 is nothing but S into L into Vs divided by 10 divided by 100 into SC. If you do this, S into L into Vs divided by 1000 S into C, right? S will be cancelled, then it is nothing but Vs into L by 1000 C. If you know this value, problem is over. Therefore, Vs into, what is the L value? Is given 10 millihenry. This is 10 milli and 10 to the power of 3 into, what is C value? 10 micro. Therefore, what is 10 micro into kilo? 10 milli. 10 milli will be cancelled. It is simply Vs. Whatever we expected, we got without any gain change. Therefore, what is this? 10 cos 100t. Therefore, what is the answer? Answer is A. This is expected. But maybe it can be, that depends on RC, RL value, gain can change, but anyway, that is also not changed. Okay, you take it. Done? Now problem number 15. Three identical amplifiers with each one having a voltage gain of 50, input impedance 1 kilo ohm, output impedance 250 ohm are cascaded. Okay. The open circuit voltage gain of combined amplifier is, this is a very interesting problem. Okay. Therefore, what is the problem is, there are three stages. Number 1, stage 1, stage 2 and stage 3. And open circuit, what is saying? There is no load connected. This is simply your V0 and this is what is our Vi. And each stage is having AV 50. This is also 50. AV is equal to 50 and AV is equal to 50 and AV is equal to 50. Okay. Then tell me, if all are in cascade, according to control systems, if all are in cascade, then what is your voltage gain, overall voltage gain? 50 into 50 into 50. What is that? 125 and 000, 1,25,000. Right? But remember, I already explained this point. Right? Even though all are in cascade, don't multiply blindly 50, 50, 50. That depends on your voltage gain, depends on source as well as load. That depends on actual load. Okay. Therefore, when I say AV is equal to 50, that is open circuit load. If there is no load and with ideal voltage source, then this is nothing but your voltage gain 50. But every stage is having input impedance, right? This is what your Ri and this is what your R0. Every stage is having Ri and R0. Therefore, for your first stage, the second stage input impedance is nothing but the load. Therefore, with respect to that input impedance, which is the load for your first stage, therefore, this is what your first stage, and this is second stage, and this is third stage, right? And let me call this as V1, small v1, small v2, okay? Then, the input impedance of second stage is nothing but load. For that, we need to calculate what is effective gain. Similarly, what is the effective gain of this? This is what your Ri and this is what your R0. I think for this there is no load, open circuit, that's what he told, and the voltage won't change, this will be 50 only. That is what we need to account and then we need to calculate. Okay. Now, the hint is, can I equivalently represent? Ultimately, we want to calculate Vi to V0. We need to calculate V0 divided by Vi of 3 stages. Okay. Then what I do, can I write equivalently? Can I replace your circuit like this? This is what is having some input impedance. This is what your Ri. Okay. And this is what you are having, the voltage gain AV into the Vi what you have here. This is what your Vi. We are having output impedance or not. This is what is your stage 1. This is your stage 1. And this is what is your V1. Now that is what is given to next stage. Therefore, this is what is your Ri. And now this is what is your AV into. Now what is this? This is what is your V1. This is your V1. Therefore, AV into V1. And this is what is your R0. Equivalently, we can represent your black box, right? Your amplifier with this. And this is your Ri. Now this is what is given to next stage. This is your Ri. And this is what is called as V2. This is V2. And now this is what is having AV into V2. And now this is what is your R0. And this is what is your amplifier, third stage. But nothing is connected, no load. That is what he told, V0. Therefore, now we need to calculate what? You know, V1 by Vi, V2 by Vi, V0 by V2. Then we'll get V0 by Vi. That is what is your voltage gain. Okay. We have only 2 minutes for the session. Okay. This is what is the hint. Just do network analysis, you'll get it. Everywhere Ri 1 kilo ohm, R0 250 ohm, AV 50 ohm. Okay. Therefore, what is the meaning of AV? If there is no load, then AV is nothing but your 50 and there is no source. Take it and then let's calculate that. Okay. Maybe you can calculate. Now we need to find ultimately. This is a network problem. You can calculate ultimately. Okay. Take it and then solve, or we will continue in the next session. Okay. Thank you.